Gogotsi, actually a PhD student from Iraq at Drexel now, and I'm delighted to be here in this beautiful city of Barcelona. I'm coming from Philadelphia, so I'm across the pond, and luckily there is a direct flight from Philadelphia to Barcelona here. Professor Patrice Simon has already talked about some of the materials we're exploring, carbon materials, and also he briefly mentioned transition metal carbides and nitrides, structures that you can see on this cover of ACS Nano, and those are the materials I'm going to talk about today. This is an entirely new family of two-dimensional materials with a variety of properties and potential applications here. So, in general, what you have certainly noticed reading the literature, working with your colleagues here, that 2D materials have been attracting an increasing application over the past decade. And certainly graphene to blame for this. Attention to graphene due to discovery of new physical properties in graphene by Andrew Geim and Kostya Novoselov actually attracted attention to the fact there are many other materials that come in a similar two-dimensional morphology. Some of them are very, very old, like clays, and those are really the most widely used two-dimensional materials today. They go into composites. They're in the bumper of every car you drive here. But many others, for example, MOFs and COFs have been produced in a two-dimensional state fairly recently. Materials that are known oxides, layered double hydroxides, have been used for a while in energy storage, from alkaline batteries to a variety of other batteries here. But what is also interesting, several materials which were not expected to exist in two-dimensional states, such as, for example, silicon, borofin, germanium, have been discovered. So what people realize that it's not only materials that exist in has a van der Waals bonded or hydrogen bond bonded weak precursor that can be delaminated, separated in sheets, can be made in 2D. That pretty much almost any material can exist in a 2D state. Moreover, this two-dimensional state brings a variety of properties, not only very high surface area, but many other properties which is drastically different from their three-dimensional counterparts here. And in 2011, we discovered that carbides and nitrides of transition metals, which were not expected, not even predicted to exist in two-dimensional state, can also be produced as two-dimensional layers here. And of course, 2D state brings a number of very interesting advantages here. We have materials now first, which have a variety of electronic properties, from dielectric to semiconductors to metals here. Atomically thick material offer flexibility and often means mechanical reliability and strength to everything from battery electrodes to thin film device applications here. And also everything is accessible, because if you have a 2D structure, the entire material is the surface here. And also, flakes of larger size with nanometer thickness combined offer surface area that can be used for ion adsorption, can be used for redox reaction, can be used for catalysis if you properly design the structure. But even more exciting with this, what is great about the 2D state? You can pile up any kind of flakes. You can combine them in any order. You can make a metallic layer, current collector. You can make other active material layer. You can make separator, which is dielectric flakes here. And you can build it by the same method. It can be deposition from solution, spray coating, anything else here. So we basically have an opportunity to create hybrid materials, build them from bricks, which are few atoms thin, or even sometimes monolayer of atoms thin, creating an entirely new generation of artificial material here. So we're very much excited. And what we're trying to do right now is to add new building blocks, new Lego blocks to a set of tools that we have available in material science here. And MXenes have been offering an opportunity to actually expand this range of materials available here. So what are these 2D carbides, nitrides, which I called MXenes, which M stands from transition metal. Those are these golden spheres. And X dark dots here stand for either carbon or nitrogen here. Those layers are just few atoms thin, just like pretty much any other 2D material. But there is a very important difference, what actually makes it different from great majority of other material to the state here. They have a truly conducting metallic core, at least most of them here. Some of them are semiconductor. There are many semiconducting 2D materials here. Graphene, which everyone praises from high conductivity, is really a zero band gap semiconductor with low concentration of carrier. Many of these materials are true metals with a high density of state at the Fermi level and with a high concentration of carriers here. But their surface is actually transition metal, which won't remain unterminated in environment. It looks like a surface of oxide or hydroxide. So you can imagine materials that combine properties of a metal being metallic with a redox active surface with atoms that can change their oxidation state and do it reversibly. Moreover, you can attach something to the surface, polymer chains, functional groups, with little effect, relatively little effect, on the electrical conductivity of the materials. If you modify graphene, for example, making graphene oxide or graphene, conductivity drops by at least 7 orders of magnitude. Here, you can attach functional groups and keep it conductive. Moreover, these materials come in 3 different flavors. We call them 2-1 structures, 2 layers of transition metal, 1 carbon nitrogen, 3-2 structures, 3 layers of transition metal, 2 carbon or nitrogens here, and 4-3. Within a year after discovery of the first one, which was titanium carbide, titanium 3C2, we demonstrated all these 3 types of structures possible. Moreover, we showed solid solution on M side, solid solution on X side, carbonitrides here. Pretty much making it potentially the largest family of 2D materials available. About 30 have been already experimentally reported, synthesized, but several dozens possible as simple compounds, and potentially millions if you consider solid solutions can be created here. So it's a very large, quickly growing family of materials here. I'm not going to talk about semiconducting properties, but for example, for this thinner structure, surface termination can pull electron density opening the band gap, so semiconducting materials are possible. But for the application I'm going to talk about, we do care, first of all, about metallic conductivity and redox here. So how do we make them? Where does the name MXene comes from? My colleague at Drexel University, Professor Michel Barzoum, is father of the group of material which are known as mixed phases or ductile machinable ceramics here. What these materials are? They are consisting of M, A element, and X carbon nitrogen. As you know, basically you can look at them as single, double, or triple layer of carbide or nitride, terminated or bonded by A element here. So what we did here is very simple here. We removed by chemical etching this layer of A element, so A is gone, MX is left, and we added a suffix in, just like a graphene, silicene, germanium to these materials here. So this is where the origin of these names here. What is important here? The bonding between MA element in these materials is either metallic or covalent, but it's not a weak van der Waals bonding. You cannot really simply separate them by mechanical exfoliation. You have to etch those materials, things here. And of course, not only mixed phases are possible as precursor, there are many other layered carbides. Oops, sorry, I have never learned how to use the clicker properly. There are many other Carbides layer, when you can remove, for example, entire layer of aluminum carbide dissolved, leaving zirconium carbide layer behind. There are other similar layered phases which are technically not max phases, like Moly 2, Gallium 2C here. So basically, message I would like to leave you with here is that there are many precursors that open road to synthesis of many materials here. And the synthesis process is actually very simple. We take ceramic powder, we dump it into a solution. Initially, we use HF, even though we now rarely use this etchant here. And what we do, we dissolve this layer of aluminum. As a result, if you look at high-resolution STEM images, layer of aluminum is gone. What is left, in this case, it's a Moly 2 titanium. So there are only carbide layers left. They're not bonded anymore. Or there is a weak hydrogen bonding because they get terminated in solution by oxygen OH group here. Naturally, now we have a precursor just like clay or LDH, where we can very simply, by either sonication or intercalation sonication, and often just simply by twisting several times a bottle with a solution, delaminate it in single layer flakes. This is a 1 liter bottle with about 400 milliliter of solution of titanium 3C2, and these flakes all look the same. So I can tell you this is graphene or moly disulfide or boron nitride. You will have to believe me, they're pretty much the same. But atomic force microscopy shows that all flakes are about 1 nanometer in thickness. So we have here single layer MXene. And reason actually why titanium 3C2 MXene oxygen terminated forms a stable colloidal solution, because there is a high negative zeta potential. For MXene, it ranges typically from -30 to -80 millivolt. So flakes stay stable in solutions that don't want to stick together. Unlike graphene, just in water, they will be floating separately here. Within about a year or two after discovery of first MXenes here, we showed that it's possible to actually get rid of HF and use benign salts like lithium fluoride or sodium fluoride, and benign acids which are cheap and non-toxic like hydrochloric acid here, to do the same etching process. Moreover, what is interesting happening? Lithium ions will go with water and intercalate between the layer of MXene sheets, giving it rheological properties of clay. So what we can do, we can etch powder, and after that take a wet slurry or dry it and add a couple of drops of water, and we get a material which we can roll right away. For example, this type of a foil. Oops, again, I'm sorry, pushing wrong buttons on the clicker here, and I'm going in the wrong direction now. Okay. I need to get back to my computer. Okay, so what you see here. This is a foil. It looks like a metallic foil, but this is just MXene sheets rolled after etching. So within 15 minutes after etching, you produce a foil which doesn't require a binder, doesn't require, of course, any conducting additive here, and looks like a metal foil. So you're making an electrode, you can right away produce it by the same way you would produce electrode for battery supercapacitors here. And we have from these materials a variety of different structures possible. Did I skip? Okay, no, I'll get a slide back here. We get a variety of different structure possible. I already mentioned to you 3 groups of M2C, M3C2, M4C3. We get pure materials. We get a random solid solution with an atom mixed here. And in 2015, we showed we can take atomic design to a next level. We can make a material in which one transition metal will be on the surface, controlling, for example, surface properties, catalytic properties of material. Another transition metal will be in the middle, largely controlling electronic properties. For example, we can make Moly 2 titanium C2 or chromium 2 titanium C2, adding magnetic and other properties to these materials here. And of course, in these layers, we can again create surface layer which will be mixed, which we have, for example, catalyst atoms surrounding by some other atoms. So we can make mix, for example, tungsten or moly surrounded by vanadium or other metal here. So there are huge opportunities for atomistic design here. So we have this very large emerging family of materials, which we can produce by simple wet chemical synthesis etching of the max phase precursors here. But you probably hear about new 2D material discovery all the time. Borofin was produced less than 2 years ago, made a lot of waves here. Still exists, I think, mainly as a monolayer on silver substrates here. Gallium nitride was produced as a monolayer under a layer of graphene and stays as a monolayer here. But very few materials from this nanomaterials world are available in larger than nano quantities. What is important in this case? We can make this material already now in 100 or even 200 gram batches in the lab here. So these are reactors developed for us by Materials Research Center in Ukraine here. And this is like a, not chocolate, this is titanium-32 MXene coming from a single synthesis batch here. And of course, there are billions of two-dimensional flakes that you can produce by dissolving in water here. And this makes a big difference. What it means that here, we can use this material not only for single flake electronic devices, small applications here. They can be produced in quantities sufficient for using batteries, supercapacitors, produce coatings on a variety of applications. And it's actually easy to do it here because when we produce a solution that you saw earlier before, it's colloidal solution, you can see Tyndall effect. We can use it as ink, actually, just in water. We can print it, do 2D printing, inkjet printing, rolling, stamping, painting here. Of course, what is important to remember, different materials will have different properties. I won't have time today to go in detail on this, but if you take this dark solution and dilute it, you will see that different colors of solution in the bottles, because different electronic properties of different MXene compositions lead naturally to different optical properties here. So there are also emerging applications, lasers, photonics, plasmonics, photocatalysis, photoelectrocatalysis, which again, I won't have time to cover here. But whenever we have a colloidal solution of single flakes, you can deal with this. It's the same way as people deal with graphene oxide or clays or any other solutions here. We can do vacuum-assisted filtration, for example, make these films with flakes aligned parallel to the surface. They'll be flexible, very nice, easy to handle here. We can spray coat them. For example, you can see here a coating on a polymer film. Coating is transparent because, for example, titanium-32 MXene absorbs about 3% of visible light per 1 nanometer. Graphene absorbs 2.3% of visible light per nanometer. So if in 1 nanometer there will be 3 graphene layers, so roughly it's a half of the absorbance of graphene. And V2C, several others are much more transparent than that. But moreover, it actually has, after solution processing, significantly higher conductivity. We get between 1 and 10,000 Siemens per centimeter, pushing to 20,000 Siemens per centimeter now. And this is done by simple, again, spray coating the film on the surface. Depending on how flakes are aligned, you will get lower on higher conductivity, denser, better aligned film. Larger flakes naturally give you higher values here. And these values are really, really high. They are higher than any solution processable material I've seen so far. And again, we are very far from the limit. And what you see here in the background is like a 5-micron thin letter size paper sheet of MXene that you can actually lift, handle, make paper airplane out of it, or of course cut it into electrodes or something else here. So basically, again, this material can be produced in large quantities and also easily processable from water solution. You don't necessarily need to use water if for your application, for example, if you want to avoid aqueous environment or mix it with polymers which are not water soluble, it's possible to use a variety of polar organic solvents which similarly can disperse MXene. And this one of my students, Kathleen Maleski, is holding Drexel logo, for example, sprayed on the coating here. So naturally, with this variety of materials, there are many emerging applications here. There is no way in remaining 10-15 minutes I can cover all of them here. But all these applications built on properties of these materials, on properties of a variety of materials in the family here. And of course, what we started with, electrochemical capacitors, and Patrice has introduced you those applications. I'm going to talk a bit more in depth on some of them. Lithium-ion, sodium-ion capacitors, lithium, sodium, magnesium, also aluminum, lithium-sulfur batteries, catalyst, electrocatalyst here, composite materials, transparent conducting coating, sensors, sorbents, water purification. They can remove lead, uranium, chromium ions, even from seawater in presence of smaller ions because of a strong interaction with multivalent ions here. Water desalination, both membrane capacitive. Plasmonics based on plasmon resonance of metallic materials here. Sensors, electromagnetic shielding, and many others. Just yesterday, I saw a new review article in Chemical Society Review appeared on biomedical application of MXenes, primarily photothermal therapy and drug delivery with those materials. So it becomes a very large range of possible applications here. And MXene research is going on all over the world now, close to 300 institutions already published papers on the subject from 30 countries here. I'm going today to talk just about 2 applications to give you a flavor of what is possible in spirit of this conference: energy harvesting and energy storage. Because much of the research we are doing at Drexel Nanomaterials Institute in my research group is related to electrochemical energy storage, but also we're looking on wearable systems, smart textiles, where we need to integrate harvesting and storage together into one system here. And of course, most of you are probably familiar with Triboelectric Nanogenerator developed by Professor Zial Wang from Georgia Tech University, and he has an entire institute in Beijing dedicated to nano energy systems now here, which allow us to take triboelectricity, basically effect most of us known from brushing, combing hair when we get electrostatic charges between 2 sliding or contacting surfaces here, which is of course a nuisance irritating everyone in a normal everyday life. It's a dangerous effect sometimes in some labs. For example, electrostatic discharge can lead to explosions when you have vapor of flammable gas in the environment, things here. But if we harvest this effect, as we all move and use electrostatic electricity for store it here to recharge our devices, develop smart clothes, power sensors everywhere here, it becomes very useful. And again, there is a lot of effort ongoing here. Why MXenes are potentially interesting here? Because of several reasons. First, as I mentioned, they have a very high metallic conductivity. Second, they can be applied from solution to any surface virtually here. In a very thin film, thinner typically that you can even deposit metal film on the surfaces where metal cannot be deposited and do it at room temperature, things here. So it's very easy to produce it, and we work with colleagues from Clemson University on demonstrating that actually MXenes can be used in Triboelectric Nanogenerator, depositing film of MXene on glass, testing it against PT, ITO films here, and basically using this mandrel, just pushing and showing. And actually in triboelectricity, you can do a variety of different motions. It can be sliding motion between the layers. It can be simply compression. As long as you bring 2 surfaces in contact with different work function, when electrons can tunnel from one surface to another, you can collect charges here. So what happens if you do it with MXene films? You see a typical tribo effect here. Voltage is going here to about 70, but actually we were able to push it about 10 times higher now voltages here. And you see the pulses produced of voltage from this contacts between the surfaces as you charge and discharge them here. And moreover, of course, when you have a material that is flexible, can do in the film here, you can potentially envision a variety of applications because you can apply it to any surface here. Again, what I'm showing to you are really very, very first experiment, very first initial work done, published just a couple of months ago here. But we showed that, for example, making flexible film and putting it on a finger, we can harvest energy from, for example, typing on your computer here, or moving hand using mouse, or typing on a PDA here. So again, if you collect and harvest this energy, and I will show you that it really works. If the movie I can make working here. Okay, so you see, well, sorry, it's not really very bright enough, but you see here, just by tapping fingers here, this array of LEDs showing MXene lightens up. So energy is being generated in every move with this material here. So it's working, it's functioning from the motion here. And this is done mechanically here, but those are again a couple of examples to show that you can simply observe really this peaks. You know, as you bend your finger, voltage is being generated. Same way, you take your smartphone, you start tapping on a smartphone, and there is energy produced. You can see a spike on oscillograph coming from just very, very light finger movement here. So again, I think this is an opportunity to produce energy in a very simple motion, pretty much anywhere, anytime, whenever we need it here. But of course, what is the challenge with all this type of, or many types of renewable energy generation here? It's a great, but to make it really useful, we need also to be able to store this energy. And when you have this type of intermittent sources, if you have short pulses, which comes in a non-basically uniform way, because you're not going to like control your motion very well, you want to actually produce energy whatever you do here and be an ensemble here. We need energy storage solutions here. And actually, supercapacitors that Patrice was talking about offer great opportunities to store charges from triboelectric, piezoelectric, other generators, because they can be charged by lower and higher voltage applied here. And I'm running awfully late, as I see from the signs that the chairman showed here. And unlike batteries, they're not limited by diffusional processes here. And Patrice expanded a little bit on this, telling that, look, double layer capacitors are great. They can be charged very quickly, but we need also redox capacitance to increase the energy density. And MXenes offer exactly this because they provide electrical conductivity with an inner layer, and they provide redox storage in transition metal in the outer layer. So it's like a oxide on steroids. You can have the same potentially energy density because you can do the same redox reaction, but you have a metal. You can also run electrons very, very quickly here. And you can make this type of films, for example, with nanotubes to loosen them up into diffusion, and you have seen this picture before here. Couple of things I wanted to stress with this. Patrice showed you this type of a reversible redox peaks. They actually come from changing the oxidation state of titanium metal. You can look at this cyclic voltammogram as a rectangle from double layer capacitance with a broad redox wave overweight. But there's almost no shift. It's electrochemically reversible after enormous rate up to 5 to 10 volts per second. We can charge it at actually 100 volts per second, and we only lose about 20% of capacitance. So we can actually have a redox process operating at rates much faster than even double layer capacitance can give you. It offers actually great opportunity for harvesting energy from very fast processes here, AC/DC filtering, and many, many other applications which actually values of charge stored being significantly larger than in double layers here. And of course, the thin films can be used to make transparent supercapacitors, for example, that will be flexible, bendable, and so on here. But Whenever we have flakes aligned horizontally, we cannot build a very thick layer. Not because we cannot build it, we can build it physically. But the diffusion paths will become so long for ions that we will get limited by ionic diffusion. And recently we also learned how to align by using liquid crystalline approach these flakes vertically. Since I have no time left, I won't go in detail, but this paper should be in press in about 3 weeks from now. I just got page proofs today, actually, of this paper, showing that if we have vertically aligned flakes, actually we can have a 35 micron film or 40 micron film or 200 micron film, and we pretty much have the same cyclic voltammogram. There's almost no change in gravimetric capacitance when we go to much thicker film. And actually, this film show capacitance, Patrice mentioned before, if you densely aligned it, in excess of 1,000 farad per cubic centimeter here. So an order of magnitude more than we can get in the same volume for double layer capacitor. So I know it was a very, very short presentation, and I probably was too superficial to cover things in detail. But few messages I would like to leave you with here. There is this wonderful, new, very large, and very quickly growing family of two-dimensional materials for potential energy harvesting, storage application, electrocatalysis, photocatalysis, transparent conducting film, solar cells, and many, many others of other application, structural composites also for energy application, multifunctional for people in this group here. It's growing very quickly. We have pure materials. We have mixed ones, solid solutions. We have layered structures here. Moreover, I didn't have time to talk about it today, but we can also control the surface chemistry, which adds another variable, another basically dial that can help you to change the properties of these materials here and affect it here. And of course, there are many exciting development possible with this here. What I would like to finish is here to show you this is my research group. This is actually a Christmas party at our place just a couple of months ago, as you understand. Those are PhD students, postdocs, a couple of family and friends who really did the work I showed to you. I would also like to send a variety of sources supporting this work. As you see, much of this research is funded from international sources and from industry, and I cannot list all the companies because some of them don't want to have their name disclosed here. And of course, research we are doing in MXene is also done with many, many collaborators. Patrice has been a great friend and outstanding collaborator over years, and we continue working on energy storage application of MXene, but there are many other people who help us with modeling and simulation of this material, with exploring specific application, biomedical, electromagnetic shielding, many others in the areas where we don't have enough expertise here. And finally, this is really my very last slide. I just, if you're interested in learning more about this material, I know I definitely could not convey all the depths needed in this presentation. Look at our review article published last year. There have actually been probably half a dozen of other reviews published since that by others. And if you want to look at the basic fundamental science behind and theoretical prediction, what is possible but has not been done yet, in my opinion, this review is the best one of available, coming from Japanese group, published also last year here, and you can download our papers from my website. Thank you very much for your attention. We'll be glad to answer questions.
Material class could take hours still to talk about. We actually used up almost all of the discussion time. I can only accept maybe one question. Any questions? Yes.
You partially answered my question, but not completely. And you said that if we have something that is very stacked, then the pathways are very long and you can align them. But can you imagine also, going back to clay chemistry that I knew about in another life, can you deposit the flakes so that they make what we used to call a house of cards structure, where you have something which is very disorganized?
Well, yes. We basically work a lot in architecture. And this work I showed at the end, for example, with liquid crystal alignment, it's a kind of this work here. We're trying to make it here. We can also make it more disordered. Just like clays, we can also pillar them by introducing large organic molecules between the layers. For example, you can use diamines, which will attach electrostatically by positively charged amino groups to the surface here. Or you can introduce, for example, tertiary amines with different lengths, hydrocarbon chains, and open spacing. So pretty much everything you know for clays can be applied to those materials. Consider them to be metallically conducting clays.
Perfect. Thank you.
Okay, let's thank Yury again. And I'm sure he's available for questions during the breaks and so forth.